Imagine you are playing a video game. Every time you make the right move, you earn points or rewards. But if you make a mistake, well, you lose points or face some kind of penalty. In the simplest sense, that's what reinforcement learning is all about. Teaching an agent like a robot, a game character, or even a self-driving car to learn from rewards and punishments. In reinforcement learning, the agent interacts with an environment. The agent takes actions, gets feedback in the form of rewards or penalties, and then updates its behavior to maximize long-term rewards. This is called trial and error learning. The goal? Get better and better at performing a task by constantly adjusting based on experience. At the core of reinforcement learning, there are three key components: the agent, the environment, the reward system. Well, the agent, this is the learner or decision maker. The environment, this is the world where the agent operates. The reward system, the feedback mechanism that tells the agent if it's doing well or not. Basically, the agent takes an action, the environment responds with new information, and the agent adjusts its future actions based on that feedback. This cycle continues until the agent becomes skilled at its task. Reinforcement learning has a wide range of applications. It's not just for gaming AI. It's being used in self-driving cars, healthcare, robotics, finance. In self-driving cars, where AI learns how to navigate roads safely. In healthcare, where AI optimizes treatment plans for patients. In robotics, where machines learn to grasp and manipulate objects efficiently. And in finance, where reinforcement learning is applied to automated trading strategies. Despite its power, reinforcement learning is not perfect. Some key challenges include exploration versus exploitation, where the agent must balance trying new things and sticking to what works. Also, computational power is another problem. Taking reinforcement learning models can take massive amounts of data and processing power. Real-world unpredictability is another issue. In highly dynamic environments, reinforcement learning models can struggle to adapt quickly. The field of reinforcement learning is rapidly evolving, with new breakthroughs happening every year. Imagine personal AI assistants that learn and adapt to your needs in real time, or AI that helps solve complex scientific problems. The possibilities are endless. For example, in robotics, robots can now learn to perform tasks like folding towels, assembling products, or even performing delicate surgeries. Now that we've got general picture of what reinforcement learning is, we can cover a little bit of the richer material, the landscape of algorithms in modern reinforcement learning, and a description of the kinds of trade-offs that go into algorithm design. Here you see a non-exhaustive but useful taxonomy of algorithms in modern reinforcement learning. As a matter of fact, it's really quite hard to draw an accurate, all-encompassing taxonomy of algorithms in the modern reinforcement learning space, because the modularity of algorithms is not well represented by a tree structure. Also, to make something that fits on a page and is reasonably digestible in an introduction video, we have to omit quite a bit of more advanced material like exploration, transfer learning, meta-learning, and that's it. Our goal here are to highlight the most foundational design choices in deep reinforcement learning algorithms. I've also provided some citations and some papers in the description of the video. At the high level, the reinforcement learning algorithms are compartmentalized in two different categories: model-free algorithms and model-based reinforcement learning algorithms. One of the most important branching points in an RL algorithm is the question of whether the agent has access to or learns a model of the environment. By model of environment, we mean a function which predicts state transitions and rewards. The main upside to having a model is that it allows the agent to plan by thinking ahead, seeing what would happen for a range of possible choices and explicitly deciding between its options. Agents can then distill the results from planning ahead into a learned policy. A famous example of this approach is AlphaGo. When this works, it can result in a substantial improvement in sample efficiency over methods that don't have a model. And the main downside is that a ground truth model of the environment is usually not available to the agent, and it's a big problem. If an agent wants to use a model in this case, it has to learn the model purely from experience, which creates several several challenges. The biggest challenge is that the bias in the model can be exploited by the agent, resulting in an agent which performs well with respect to the learned model but behaves suboptimally in the real environment. Model learning is inherently difficult, so even significant effort, dedicating extensive time and computational resources may not always yield success. Algorithms that utilize a model are known as model-based methods, while those that don't are called model-free methods. Although model-free approaches sacrifice the potential improvements in the sample efficiency that a model provides, they are generally easier to implement and fine-tune. At the time of recording this video, model-free methods have been more widely adopted, developed, and tested than model-based methods. Another critical branching point in an oral algorithm is the question of what to learn. The list of usual suspects includes policies, either stochastic or deterministic, action value functions or Q functions, value functions, and environment models. So now the natural question is what to learn in model-free reinforcement learning. There are two main approaches to representing and training agents with model-free reinforcement learning: policy optimization and Q-learning. The primary strength of policy optimization methods is that they are principled in the sense that you directly optimize for the thing you want. Q-learning methods gain the advantage of being substantially more sample efficient when they do work, because they can reuse data more efficiently than policy optimization techniques. Regarding the model-based reinforcement learning algorithms, unlike model-free ones, there aren't a small number of easy-to-define clusters of methods for model-based reinforcement learning. There are many orthogonal ways of using models. I'll give you a few examples, but the list is far from exhaustive. In each case, the model may either be given or learned. Pure planning, the most basic approach, never explicitly represents the policy and instead uses pure planning techniques like model predictive control to select actions. In MPC or model predictive control, each time the agent observes the environment, it computes a plan which is optimal with respect to the model, where the plan describes all actions to take over some fixed window of time after the present. Future rewards beyond the horizon may be considered by the planning algorithm through the use of a learned value function. The agent then executes the first action of the plan and immediately discards the rest of it. It computes a new plan each time it prepares to interact with the environment, to avoid using an action from a plan with a shorter than desired planning horizon. The other one is expert iteration, which is a straightforward follow-on to pure planning, which involves using and learning an explicit representation of the policy. The agent uses a planning algorithm like Monte Carlo tree search in the model, generating candidate actions for the plan by sampling from its current policy. Then the planning algorithm produces an action which is better than what the policy alone would have produced. Hence, it's an expert relative to the policy. The policy is afterwards updated to produce an action more like the planning algorithm's output. AlphaZero is one example of this approach. And another one is data augmentation for model-free methods. In this case, we use a model-free reinforcement learning algorithm to train a policy or Q function, but either augment real experiences with fictitious ones in updating the agent or use only fictitious experience for updating the agent. An example of using purely fictitious experience to train the agent is world models, which they call training in the dream. Another approach is embedding planning loops into policies, which embeds the planning procedure directly into a policy as a subroutine so that complete plans become side information for the policy, while training the output of the policy with any standard model-free algorithm. The key concept is that in this framework, the policy can learn to choose how and when to use the plans. This makes model bias less of a problem, because if the model is bad for planning in some states, the policy can simply learn to ignore it. To learn out more, I highly recommend you to check out my other videos regarding reinforcement learning.